But we could talk about horizontal asymptotes too, okay? So a horizontal asymptote, let's take a look at this graph here, okay? You can see that there's a horizontal asymptote at y equals 0, okay? What you're doing is you're saying, what is happening to the graph as x gets really, really, really small, and what's happening to the graph as x gets really, really large? Because as x gets really, really large, you can see that we're approaching y equals 0. And the same thing is true here. As x gets really, really small, we're approaching y equals 0. Okay, let's take another example. I'm gonna add in an x plus 1 here. I'm just going to change the function a little bit so that you can see that you can have something different. So over here, you can see as x gets really, really, really small, or as it goes to negative infinity, we're not approaching 0 anymore, we're approaching 1. And here the same thing is true. We're not approaching 0 anymore, we're approaching 1. So we have this horizontal asymptote. Okay, so remember what we're asking. We're saying what happens to the graph as x approaches negative infinity, and what happens to the graph as x approaches positive infinity. Okay, and that's going to tell us where our horizontal asymptotes are. And I want you to just be aware that sometimes we don't have horizontal asymptotes. Okay, so on rare occasions we won't have horizontal asymptotes. So let's figure out how we determine this. Okay. And this is a longer explanation, but it's just as simple a process. In the end, it's even simpler than vertical asymptotes. So it's a longer explanation, but once you understand what's going on, then it's a much faster process, okay? So let's look at horizontal asymptotes. And there are really 3 possibilities. So to find these, what we're doing is we're asking what happens to y as x approaches negative infinity. What happens to y as x approaches positive infinity? Now there's something else important to know. Let's go back in here. This function here is an example of where there are 2 vertical asymptotes. So this is another function, okay, another reciprocal function. So notice it looks a little bit different. We have this extra piece in the middle, okay? This looks almost cubic, right? But here we have 2 vertical asymptotes. So this function was x over x squared minus 25. So if we factor the bottom, we get x plus 5 times x minus 5. So we can see that we have 2 vertical asymptotes, 2 places where the x value doesn't exist. X squared minus 25 is x plus 5, so that means that we don't have an asymptote at negative 5. Sorry, we don't have an x value at negative 5, times x minus 5. So we don't have an x value at x equals 5, okay? So we have 2 vertical asymptotes. This is what it looks like. Okay, we're approaching negative, our y values approach negative infinity and positive infinity at x equals negative 5, and then the same thing at x equals 5. Now, the reason why I mention this is that you could have two vertical asymptotes. You cannot have two horizontal asymptotes, okay? So think about it. If we had a second horizontal asymptote, that would mean that two things are happening as we approach, as our x value approaches negative infinity or positive infinity. That can't be, okay? Why can't it be? Because this is a function, okay? Functions, that can't happen. Let's go back to y equals 1 over x. Right? Only one thing could happen. It can only approach one line. Because if we were also approaching, let's say 10, then the problem is we would have another part of the graph over at y equals 10, and that's not possible. This is a function. In order for it to be a function, only one thing can happen as x approaches positive or negative infinity. Here, we have two vertical asymptotes. That's okay, because it'll still pass the vertical line test. Okay? If we have two horizontal asymptotes, it won't pass the vertical line test anymore. So that's just an important note as well. So there can only be one horizontal asymptotes. I should say there can be no more than one, because sometimes you don't have one. And that's because it wouldn't be a function otherwise. So let's take a look at some reciprocal functions and see what's going on, okay? We're looking at rational functions. Reciprocal and rational are the same thing. We're using them interchangeably here, okay? So if we take a look at f of x equals 1 over x, what we're saying is what happens to f of x? As x gets very, very large. Now we know a horizontal asymptote, okay? The same thing is going to happen as x gets very, very small, as x approaches positive infinity or negative infinity. We're just talking about positive or negative numbers, essentially. Okay. So if we plug in a very large number into the denominator, like 1 over a billion, this is very close to 0. Right? So our denominator increases, and as it increases, 1 over x gets closer and closer to 0. If we had 1 over a trillion or 1 over quadrillion, it gets very, very, very close to 0. Okay? So that would mean that our y is very close to 0. We're approaching y equals 0, but we never actually reach y equals 0. We never get to 0 because our numerator is 1. So we have a horizontal asymptote at y equals 0. Let's take another example. Let's say that we have f of x is equal to 1 over x squared. Well, we're asking ourselves the same thing. We're saying, well, what happens to f of x as x gets very, very large? Remember, f of x is like y. Well, as x gets really, really large, we have 1 over a very, very large number. It's very close to 0, but it doesn't reach 0. So again, our horizontal asymptote is at y equals 0. Let's take another example. Let's say that we have f of x is equal to x over x cubed. Okay. Well, once again, we can simplify this. This is the same thing as 1 over x squared. Okay, one of the x's cancels. And once again, as x gets very, very large, we still have 1 over a very large number. So our asymptote is once again at y equals 0. Okay. And just a quick note, your vertical asymptote is also at x equals 0, because if x were equal to 0, then this would be undefined. Okay, so we have a vertical asymptote here as well. Okay, let's take another example. Let's say that we have f of x is equal to x squared plus 1 over x cubed plus 2x. Okay, well, this is another case. But what we're doing is we're saying we have a very, very large number squared plus 1. Well, a very, very large number squared plus 1 is really just a very large number squared, okay? The plus 1 is insignificant. It doesn't change a very large number. The same thing is true of plus 2x. A very, very large number cubed plus 2 times that number, well, the very large number cubed dominates, okay? The plus 2x becomes insignificant compared to the x cubed. So we can ignore them. So notice I'm going to write this differently. I'm not canceling, I'm not crossing it out the way that I usually would. I'm putting an x through it, okay? So why are we doing that? The plus 1 in the numerator and the plus 2x in the denominator are insignificant compared to x cubed and x squared, or really x squared and x cubed. So we can ignore them. So what we're doing is we're saying, hey, this is not equal to, okay? We're not using an equal sign. This is going to look the same as x squared over x cubed. But this simplifies down to 1 over x. And 1 over x, we know, is 1 over a very large number. So we have a horizontal asymptote, which I'm going to abbreviate as HA, at y equals 0 again. Which means that we're kind of coming to a conclusion. We're saying if the denominator grows faster than the numerator, okay, then the horizontal asymptote is at y equals 0, because we wind up just simplifying to 1 over a very large number. Okay, how do we know if the numerator is growing faster than the denominator? We can look at the degree here. So the degree of the denominator is 3. The degree of the numerator is 2. The degree of the denominator is greater than the degree of the numerator. So the denominator is growing faster, okay? So let's write that in as one of our big conclusions. I'm gonna put that in blue. If the degree of the denominator is greater than the degree of the numerator, then the denominator is growing faster than the numerator. So the horizontal asymptote is at y equals 0. Okay, so this is our first big thing, okay? This is our first possibility. But then we have other possibilities, right? Because sometimes it doesn't simplify to 1 over a very large number. Sometimes it simplifies to something else. So let's take an example of f of x is equal to x, for example. Let me do that in black. Now, I know what you're thinking. You're thinking, but hey, this isn't a reciprocal function. And you're right, it's not a reciprocal function. And we can see that because we don't have any asymptotes here, right? Vertical asymptotes, there are no vertical asymptotes because there's no denominator equal to 0. And think about what happens as x gets very, very large. As x gets very, very large, y gets very, very large. Nothing happens to y. We don't approach anything. So here, as x gets very, very large, so does y. Y doesn't approach anything here. It just gets really, really large. So there is no horizontal asymptote. So let's take another example. Let's say we have f of x is equal to x cubed over x. Well, this is the same thing as x squared. So once again, as x approaches infinity, so does y. There is no horizontal asymptote. Okay. Now we have another possibility. We have f of x is equal to 2x to the 5th minus 20x to the 4th plus 6x cubed minus 4 over 3x to the 4th minus 2x to the 5th, x to the 3rd plus 23x squared plus 8. Now this seems so complicated, right? But the only thing that's significant are the first terms, okay? The terms with the leading coefficients. And the reason why is that x to the 5th is so much larger than x to the fourth that all of this other stuff is insignificant. So again, the only terms that matter are the ones with the highest power of x. Because the others are so much smaller. That we say they're insignificant. So what that means is that once again, we're not using an equal sign because the function is not exactly the same, okay? What we're saying is that this can be interpreted as 2x to the fifth over 3x to the fourth. And it can be interpreted that way when we're trying to figure out what happens when x gets very, very large. Because when x gets very, very large, these don't influence it at all. And what we wind up with here is 2x over 3. There is no horizontal asymptote. Which means that we come to another big conclusion. We look at the degree again. If the degree of the denominator is less than the degree of the numerator, then the denominator is growing more slowly, okay? Or we could switch it around and say if the degree of the numerator is greater than the degree of the denominator, then the numerator is growing faster, which means there is no horizontal asymptote. So you see what happens here, that it's a lot more explanation, but there's really these two possibilities, okay? And we'll have one more. There's a third one. So let's write down that. If the degree of the numerator, so we're looking at which is growing faster. Is greater than the degree of the denominator, that means the numerator is growing faster. So there is no asymptote, no horizontal asymptote. And actually, that would also mean that there's no vertical asymptote. There might be, no, there's no horizontal asymptote. There might be a vertical asymptote. Then there is no horizontal asymptote, okay? Which makes sense because these aren't even reciprocal functions anymore, okay? So then we have one more possibility. The last possibility is what happens when they're growing at the same rate, right? So in one case, we're talking about the numerator growing faster than the denominator. In the other, we talk about the denominator growing faster than the numerator, but they can also grow at the same rate. So let's take an example of that. Let's say that we have f of x is equal to x over 2x. Well, think about what happens here. What happens is that the x's will cancel and we get 1/2. So this is saying, hey, as x gets really, really large, our y is 1/2. So that means that we have a horizontal asymptote. At y equals 1/2. Right? Because it doesn't matter what x is. X could be huge, but it's canceling out. So we get 1/2. So we're saying as we approach this, we get 1/2. And let's see what that looks like on a graph. So we have x divided by 2x. And you could see that this is y equals 1/2. And we just have a line here. And that's fine. And you can see that at x equals 0, actually, at x equals 0, it's undefined, which makes sense because it's x over 2x. And at x equals 0, it would be an undefined fraction, and it's undefined. Notice it's not a vertical asymptote, it's a whole because the x's cancel. Okay, so when the x's cancel, we get a whole, and we have a vertical asymptote at 1/2. Let's take another example. Let's say that we have f of x is equal to 5x over 7x. Well, if you notice, once again, your x's cancel. This becomes y equals 5 over 7. So your horizontal asymptote is at y equals 5 over 7. If we have f of x is equal to 3x squared over 12x squared. Okay, notice they're growing at the same rate. The degree is the same, so they're growing at the same rate. The x squares cancel. You're left with 3 over 12, or 1 over 4. So your horizontal asymptote is at y equals 1 over 4. And if we look at it where we have other terms, let's say that we have 7x to the 4th plus 8x squared minus 10x plus 3 over negative 6x to the 4th minus 2x cubed plus 70x. Okay, notice what happens again. These terms becomes insignificant. The only terms that matter are the first two. Okay, the terms that we crossed out are insignificant. When x is very large, because 7x to the 4th is so much larger. So what that means is that this, again, we're not using an equal sign, it's not equal. It's just saying that this will look the same as 7x to the 4th over negative 6x to the 4th. The x to the 4th cancels, and you have 7 over negative 6. So your horizontal asymptote is at y equals -7/6. Okay. So now we have another conclusion. If they're growing at the same rate, meaning the degree is the same, then what we could do is we could look just at the leading coefficients, right? It's the ratio of the leading coefficients here, because the x's cancel, whether it's x to the 4th or x to the 7th or x to the 200th, they'll cancel. So all we need to look at is the leading coefficients. So this is the last case. If the degree of the numerator equals the degree of the denominator, that means the numerator and denominator are growing at the same rate. Asymptote is the ratio of the leading coefficients. Meaning xy equals the leading coefficient of the numerator that's horizontal asymptotes. Now there's one other type of asymptote, and that's a slant asymptote. So let's take a look at this graph here. So what you see here is there is a vertical asymptote here. Okay? We approach a vertical line on both sides. There's also a horizontal, slant asymptote, diagonal asymptote that we're approaching. So this is a line that's approaching, and this is a line that's approaching. So we could have a slant asymptote, okay? And here's how we find that. And it's called a slant or an oblique asymptote. Now, it only exists, okay, if the degree of the numerator is exactly one more than the degree of the denominator, okay? And the reason for that is that in order to find it, we divide. And when we divide, we look at the quotient, okay? So let's write this out. Only exists if the degree of the numerator is one more than the degree of the denominator. can't have both a horizontal asymptote and a slant asymptote for the same reason, okay? That it wouldn't be a function. You can also see it from what I'm about to write, or what we just wrote. I'm going to finish what I'm writing. Okay, you can see it from here that you can't have both, because we already know that if the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. And this is saying a slant asymptote will only exist if the degree of the numerator is one more than the degree of the denominator. Okay, so you can't have both a horizontal and a slant asymptote. And the way that you find the slant asymptote by dividing. And the asymptote is y equals the quotient. So let's explain why this is true, okay? The dividend over the divisor equal to the quotient plus the remainder over the divisor. Now we know something. We know that when x is very, very large, this approaches 0. Because the remainder, or let's write it as the degree of the divisor is greater than the degree of the remainder. Quotient plus 0 is just the quotient. So the dividend over the divisor approaches the quotient as x gets very, very large. Okay, let me explain that one more time. We know that in any function f of x, the dividend over the divisor is equal to the quotient plus the remainder over the divisor. We've talked about this a lot when we were doing long division and remainder theorem, factor theorem, we talked about this. So here what we're saying is that the degree of the remainder is less than the degree of the divisor. Now, if that's true, then we know that when x gets very, very large, this approaches 0. We know that from everything that we talked about with the horizontal asymptotes. So that means that the dividend over the divisor is actually equal to the quotient plus 0, or something very, very close to 0, okay? Which means that as x gets very, very large, this is approaching the quotient because this is getting closer and closer to 0. So this is kind of a proof of you find the slant asymptote by dividing, and the asymptote is just y equals the quotient. Because when you divide, this gets very, very close to 0. So we're approaching the quotient. We never reach the quotient because this is never 0, okay? It can't be 0 if the degree of the numerator is greater than the degree of the divisor, right? Then you're always going to have a remainder. It's never going to not be a remainder, okay? And even if it is a remainder, then this is, sorry, let me be clear. There might be a case where the remainder is 0, but even then, right, it's still that it's y equals the quotient. Okay. So let's just do one example of this, okay? So let's say that f of x is equal to x squared minus x over x plus 1, okay? Well, the degree of the numerator equals 2. The degree of the denominator is equal to 1. And 2 is equal to 1 plus 1. So there is a slant asymptote. So now we're going to divide x plus 1 into x squared minus x. Don't forget the plus 0 at the end. Okay. X goes into x squared, x times. We multiply, we get x squared plus x. Okay, we're just doing long division. I'm not going through and doing a long explanation of this because we've done it so many times. We subtract, the x squared cancels. Negative x minus x is negative 2x. So we have negative 2x plus 0. How many times does x go into negative 2x? Negative 2 times. Now we could really stop here because we know that the next set is going to give us the remainder, but let's keep going. We got negative 2x minus 2, and if we subtract, 0 minus negative 2 is 2. So we have a remainder of 2, but we don't really care about the remainder. All we care about is the quotient. So this last set of subtraction is kind of, it's irrelevant. So our slant asymptote is that y equals x minus 2. Okay, and just so that you have it, our vertical asymptote, remember this is where the denominator is equal to 0. So our vertical asymptote is that x equals negative 1. Okay. Let's take another example. Let's say that we have f of x is equal to x squared minus x minus 2 over x minus 1. So again, here, the degree of the numerator is equal to, it's equal to 2. The degree of the denominator is equal to 1. 2 is equal to 1 plus 1. So we divide x minus 1 into x squared minus x minus 2. X goes into x squared, x times. Then we wind up with an x minus x here. And this cancels, right? X squared. Both of these actually cancel. Okay. So all that we're left down here with is just a negative 2, and we're done. We can't divide x into negative 2. So our slant asymptote is at y equals -2, and our vertical asymptote is at x equals 1. Okay, there is no horizontal asymptote. Notice the slant and the horizontal asymptotes are y equals, whereas the vertical asymptotes are x equals. Okay, let's take one last one. Let's say that we have f of x is equal to 3x squared plus 1 over x. Okay. Again, the degree of the numerator is 2. 2 is equal to 1 plus 1. So we do have a slant asymptote. That's what we're saying here. And in this case, we divide x into 3x squared plus 0x plus 1. Okay, how many times does x go into 3x squared? 3x times. And I'm sorry, this should be x plus 0, right? Because we have to make it in standard form. So plus 0x. We subtract. This should be an x squared, 3x squared. And once again, both of these things cancel. Okay, and what you're left with is just like here, you're just left with a 1, but that's irrelevant because that's the remainder, so we don't care about that. So here, the slant asymptote is at y equals 3x. It's just the quotient, and the vertical asymptote is at x equals 0. And just so that you see what that looks like, if we graph 3x squared plus 1 over x, and I'm going to also put in y equals 3x, just so that you see what it looks like. Okay, so you could see that this graph is approaching x equals 0, but it's also approaching the line y equals 3x. We could see that graph gets very, very close to 3x, but it never touches it. Okay. And let's just take some random functions. Let's say that we have holes. Sometimes holes are called discontinuities. Okay, so holes, which are discontinuities because the function doesn't continue through it. Horizontal asymptotes. And the slant asymptotes. So let's just do a couple of examples of those. So let's say that we have f of x is equal to 6x cubed minus 7x squared plus 2x minus 4 over x minus 5. So the 6x cubed minus 7x squared plus 2x minus 4, I'm going to tell you it's not factorable. Okay, certainly it's not divisible by x minus 5. We can tell that, remember, in two ways. We could either divide by x minus 5, or we could plug in 5 here, and you could see pretty quickly it's not going to give you 0. Okay, you could plug it in, but it's not going to give you 0. So the only reason for factoring the numerator is to see if that x minus 5 would cancel, and it's not. Okay, so that means that at x equals 5, there's a hole. Not a hole, a vertical asymptote. Okay, so at x equals 5, it makes the denominator 0. And an x minus 5 doesn't cancel, so it's not a whole. Our horizontal asymptote if we look at the degree of the denominator, it's greater than the degree of the numerator. So there isn't any. Remember, there are three possibilities. There's the possibility where the numerator is greater than the degree of the denominator, okay? Then there's no asymptote. Where the degree of the numerator is less than the degree of the denominator, in which case the asymptote is 0, or where they're equal, in which case the asymptote is at y equals the ratio of the leading coefficients. And slant asymptote, there's also no slant asymptote here. The degree of the numerator is 3, and the degree of the denominator is 1. 3 is not equal to 1 plus 1. Okay. Let's do another example. Let's take f of x is equal to x squared, 2x squared, plus 5x minus 3, and then x squared plus 7x plus 12. So we're going to factor this. I'm not going to spend time on the factoring. We have 2x minus 1 times x plus 3. And then we have x plus 4 times x plus 3. So the x plus 3 over x plus 3 cancels. So here's what that tells us. That tells us that there's a hole at x equals negative 3. And that's because x plus 3 is in the denominator. So x equals negative 3 would make the denominator 0. Right? But x plus 3 cancels, giving us a whole instead of an asymptote. So we're still saying x can't be negative 3, okay? It's just that we have a hole there instead of an asymptote. Now we still have a vertical asymptote because we still have x plus 4 in the denominator and it doesn't cancel. Okay. So x equals negative 4, it makes the denominator 0, but x plus 4 doesn't cancel. Now let's look at the horizontal asymptote. Well, the degree of the numerator is 2. The degree of the denominator is 2. So they're equal, which means that we do have an asymptote. The leading coefficients of the numerator is 1. The leading coefficient of the denominator, leading coefficient of the numerator is 2. Leading coefficient of the denominator is 1. So our horizontal asymptote is at y equals 2. I'm going to abbreviate leading coefficient as LC. Okay, everything else gets ignored. Everything else becomes irrelevant. So the x squareds cancel and you're left with 2 over 1. And for the slant asymptote, there is no slant asymptote, primarily because there's a horizontal asymptote. Reasons. The degree of the numerator is not 1 plus the degree of the denominator. And if there's a horizontal asymptote, there's no slant asymptote. It wouldn't be a function otherwise. And that's it. So you can identify all of these using that. So we can do that with any function, okay? So you factor it, that's gonna help you find the holes and the vertical asymptotes. And then you're looking at the degrees in order to determine the horizontal asymptote. And then for the slant asymptote, again, you're looking at the degrees, but then you're dividing, okay? And that's it. So remember, if you have questions on this lesson, please, please, please post to Blackboard in the discussion that gets created. Okay. That's it for rational functions. By the way, the next thing that we're going to look at is transformations. And so your next quiz it will cover up to this video, and that's it.